Today we will see particle in a box, that is one-dimensional infinite square well potential. Consider the motion of a particle of mass m confined to move between two walls of infinite height at x equal to 0 and x equal to L. Particle in a box is regarded as the electron in a metal. The background of the positive ion provides the attractive one-dimensional well in which they move. So, the electrons are considered as the quantum particles represented by wave functions trapped in a metal box, or it can be considered as the electron moving in one dimension and a positive force acting in opposite direction. So, this is the particle in a box. Here the width of the box is L. Since there is no force between the particle and the box, the potential energy V of the particle is 0 inside the box. That is, we know that force F is equal to minus dV by dx. Here there is no force between the particle and the walls of the box, so F equal to 0. It implies V is a constant. V is a constant. For convenience, we take V equal to 0 inside the box and V equal to infinite outside the box. That is, the particle is completely excluded outside the box. Here V equal to 0, that is, the potential is independent of time. So, we take Schrödinger's time independent equation, that is d square psi by dx square plus 2m by h cross square into a minus v psi equal to 0. This is Schrödinger's time independent equation. Here v equal to 0 inside the box. Therefore, the equation becomes d square psi by dx square plus 2m by h cross square e psi equal to 0, and put k square equal to 2m e by h cross square, that is, this is equation 1. Therefore, the above equation reduces to d square psi by dx square plus k square psi equal to 0, that is equation 2. And the solution of this differential equation is psi equal to a sin kx plus b cos kx. Next, we apply the boundary conditions, that is psi equal to 0 at x equal to 0 and psi equal to 0 at x equal to L. That is, there is no interaction between the particle and the walls. So, psi equal to 0 at the walls boundary, that is at x equal to 0 and x equal to L. Then applying the first condition, that is psi equal to 0 at x equal to 0. Then the equation, that is the solution psi equal to a sin kx plus b cos kx, that is equation number 3. It reduces to 0 equal to a sin kx, that is sin 0 plus b cos 0. Therefore, 0 equal to sin 0 is 0 and cos 0 is 1. So, we get b equal to 0. Therefore, equation 3 becomes psi equal to a sin kx, that is b is 0, that is equation number 4. Then applying the second boundary condition, that is psi equal to 0 at x equal to L, that is the second boundary condition. Therefore, psi equal to 0, a sin at x equal to L, that is a sin kL. So 0 equal to A sin KL. Either A equal to 0 or KL equal to 0. So we exclude A equal to 0 because if A equal to 0, psi equal to 0, that is impossible. Therefore sin KL equal to 0, that is KL equal to n pi. So the solution becomes psi equal to A sin n pi by L ex. That is K equal to n pi by L. And applying the normalization condition, we get A equal to root of 2 by L. That is psi equal to root of 2 by L sin n pi by L ex. So this is the wave function for the particle inside the box. That is psi equal to root of 2 by L sin n pi by L ex. Next, we compare the equations. First, k square equal to 2m e by h square and the equation KL equal to n pi. That is comparing the equations 1 and 5. That is k square equal to 2m e by h cross square, and from equation 5 KL equal to n pi, that is k equal to n pi by L or k square equal to n square pi square by L square. Then comparing these two equations, we get 2m e by h cross square equal to n square pi square by L square. That is E equal to n square pi square h cross square by 2m L square. Here we know that h cross equal to h by 2 pi. So E equal to n square pi square h square by 4 pi square 2m L square. So pi square can be cancelled. Therefore E equal to n square h square by 8m L square. So this is the value for energy of the particle inside the box. That is E equal to n square h square by 8m L square.